Thank you, Alex. Hello, everyone. So I'm Maury from BRGM, and with Francesca from Ineris, we will present you what we did for a good practice guide in France for managing seismicity induced by deep geothermal operation. If you can go ahead, please. So to begin with, before going into detail about the guide, we'll give you some definition. We based our guide on about deep geothermal energy. And so we did some classification of deep geothermal. It was initially based on the MOC play type definition. And so we did some adaptation to separate the geothermal reservoir into three main categories based on the geological control on natural permeability. So the first category is a matrix porosity and permeability control system. So the blue one that are the less deep and less hot, like for example, sedimentary basin in the Paris basin. Next, there is a mixed control system, so such as the Molas basin. And the third one that encompasses several of MOC play type definition are the fault and fracture control system that could cover active volcanism such as in Iceland and extensional domain in Upper Ringgraben in France, for example, or Germany, and also basement type such as in Australia. So those are our three main categories. And then if you go to the next slide, we have also some definition about exploitation approach. So we separate two exploitation type, the geothermal site that consists in one production well and two or three reinjection well. And also there are the geothermal field. So the difference is there are many injection and production wells, such as in oil and gas, for example, but for geothermal energy. And also the technology, you can have technology to improve the production or reinjection of the fluid. So this is what we call the EGS technology that encompass all type of stimulation, hydraulic, chemical, or thermal.
Yes, so thank you, Julie. And now I will focus more about the characteristic of induced seismicity linked to deep geothermal operations. So what we know is that most of the time the deep geothermal exploitation is linked to microseismic activity, which means that events are of low magnitude, generally smaller than 2, and that these events are not felt at the surface. This microseismicity is even inherent to some operation of deep geothermal project, especially when we use stimulation, as Julie just explains, because in this operation, basically we have shearing along pre-existing structures in order to enhance the permeability of the reservoir. So just to give you an example, in this image you can see the seismicity related to different stimulations of the deep wells of Sulfuré project in France. For each of these simulation, we had several thousand seismic events, of which most of them, or even all of them, are microseismic events, which means that they are characterized by very low magnitude. However, in some cases, deep geothermal operation can be related to larger events. It has been, for example, also the case in Sulz for some events which have been felt by local population. In this case, we introduced what we have defined seismic incidents, which is for us seismic events whose intensity is likely to cause nuisance or damage to infrastructure, and which can affect the execution or even the continuation of the geothermal project. So just to give you some examples of seismic incidents, the first example is, of course, related to the seismic activity linked to the geothermal project in Pohang in South Korea. This is the largest, so far, the largest seismic event related to deep geothermal operation, a magnitude 5.5, which occurred after several simulation operation in the deep wells of the project, and which caused several injuries, 1 fatalities, and more than $70 million of damages. After these events, the project was stopped. Another example in Europe is the case of Basel, so an event of magnitude 3.4, which caused several million euros of damages, which occurred just after the end of the injection operations, and after that also the project has been stopped. In France, the most recent seismic incident is related to the GeoVen project in Vandenheim, close to Strasbourg. Here, the first felt seismicity occurred occurred in 2019, more or less 5 kilometers south of the geothermal doublet. However, the largest events occurred close to the wells, with a first event of magnitude 3.6 in 2020, after which the local authority asked for the stop, for stopping the operation, and after that the seismicity has been still persistent, with the largest event which occurred more than 6 months after the shutting, so after the injection operation. So all these examples explain that, of course, it's very important to manage induced seismicity in deep geothermal operation. And in order to manage, the aim of managing geothermal induced seismicity is, of course, to try to avoid as much as possible the occurrence of these seismic incidents by minimizing the magnitude of the induced events while allowing operation to proceed. Of course, in doing this, there are some challenges in managing geothermal induced seismicity. First of all, the induced seismicity is the result of a complex mechanism due to the interaction between different factors, which are natural and anthropogenic. So it's a difficult phenomenon to control. And then also we have some aspects which are really related to the operations in deep geothermal exploitation, such as, for example, the fact that sometimes we need to target fault zone during injection operation, which can potentially increase the seismic hazard. The fact that also these that geothermal wells are generally located very close to urban areas. So we have larger people and infrastructure which are exposed to seismic hazard, and also the fact that in geothermal induced seismicity can occur several hours, days, or even some weeks after the end of the injection operations. So in this context, it is clear that we need good practices and guidelines in order to be able to manage this complex phenomenon. And this is basically the aim of the guide that we have produced for France. So this guide has been commissioned by the Ministry of Ecological Transition and Energy Transition to Ineris and BRGM. This has been commissioned after the seismic incidents in Vandenheim, so near Strasbourg. The guide wants to, it's mainly addressed to operators, administration, and all other stakeholders which are involved in the field. In the guide, we try to cover different types of geothermal reservoirs, as Julie showed you in the beginning of the presentations. So all the 3 different main type of geothermal systems. And with this guide, what we try to provide is a methodology to assess seismic incident hazard along the whole life cycle of a geothermal project, so from exploration to shutdown of a site, and also to propose prevention strategies and mitigation measures to be which are adapted to the level of seismic incident hazard of the project. So here you can see the general content of the guide. So we have the first chapter, which gives general definitions about geothermal system and exploitation methods, and as well about induced seismicity, generally induced seismicity, and in particular linked to geothermal operations. And then what we have done is that we have realized a worldwide review of deep geothermal projects, which can be related or not to induced seismicity. The aim of this worldwide review was to try to identify intrinsic and operational factors which can influence the occurrence and the intensity of the induced seismicity. So then, based on the lesson learned on the analysis of this case study review, we have defined our assessment methodology to define the level of seismic incident hazard for a deep geothermal project per different key phase of the project. And then we also give some recommendation in terms of reservoir characterization and monitoring, and in terms also of TLS protocols. So in the next slide, we will mainly focus on this part of the guide. So for what concerns the lesson learned from the case study review, what we have done is that we have selected about 50 deep geothermal projects which are located in Europe and around the world. These projects are classified based on the 3 types of geothermal system which we have defined before. So you can see them in different colors in the map. And we have chosen this project in order to select projects which can be for which seismicity has not been observed. So some of these projects are not related to induced seismicity, while other of these projects can be characterized by different episodes of seismicity with variable magnitude. So we can have microseismic events as well as seismic incidents. So the first results which came out from the case study review is that the seismic response is largely variable according to the type of geothermal system. So what we observe, so here on the left of the chart, you can see the projects which are not related to induced seismicity, and on the right you can see projects related to induced seismicity, which are indicated for which we have indicated the maximum magnitude which have been recorded. So what we observe is that matrix porosity and permeability controlled system are generally not linked to induced seismicity, at least for the project in this category that we have selected. Then mixed controlled systems that are the ones in yellow, orange, can be sometimes related to seismicity, but this seismicity remain of low magnitude, generally smaller than 3 if we exclude the St. Gallen case, which is a particular case. And then on the other side, we observe that fault and fracture controlled systems are more often characterized by seismicity, which can be of higher magnitude, so larger than 3. What we have done is then that we have tried to analyze other factors intrinsic, so related to the tectonic and geologic setting in which the different projects are and also operational factors such as exploitation method, operation type, injection volume, and so on. And for each of these factors, we try to analyze on which extent they have an influence on the intensity and occurrence of the induced seismicity. I will not go into much detail about this analysis. We can discuss about it later in the discussion if you want. What we want to give here is the main conclusion given by the case studies review is that, of course, we wouldn't try to find a single parameter correlation, because, of course, seismicity is a complex phenomenon which cannot be explained by a single parameter correlation. But the aim of this analysis was to try to associate a deep geothermal project to a different level of seismic incident hazard in function of the intrinsic and operational characteristics and on the type of exploited reservoir, so the type of geothermal system. So this chart try to summarize the conclusion given by the case study review. The first aspect that we observe is that the seismic hazard is low when we are exploiting porous aquifer in the absence of faults and when we are not using EGS technologies. The seismic hazard can be considered as medium when we are exploiting mixed control reservoir in the presence of faults which are, however, not connected to the basement and in which we are not using EGS technologies. And then we can consider that the seismic hazard is higher for all type of geothermal system when these are characterized by good hydraulic properties, but when we are in presence of faults which can be critically stressed and or which can be connected to the basement. Then also the other aspect which represent a higher seismic hazard is in faults and fracture controlled system, which present low natural fluid flow and low injectivity when we use EGS technologies and when the net volumes injected volumes are large. So this is especially for geothermal fields. So these results of the case studies analysis has been then used in order to define the criteria for our methodology for assess the seismic hazard.
So yes, I will present now this methodology. So go. Oh, yes, thank you. So the basic principle of this method that we developed for the seismic incident hazard assessment, so it needed to be applicable to all geothermal systems and all technologies used, well, in France, but most of them are used. It was based on logic tree. Why? Because we wanted to take into account the interaction between indicators, but without defining a scoring system. And it allows us to define the level of seismic incident hazard for different key steps of a geothermal project. So the idea was to have an iterative evaluation. And the approach of the guide was to choose our indicator and build our logic tree based on the result of the case study review that Francesca just presented. And depending on this level of seismic hazard, we provide recommendation in terms of data acquisition and parameters to be monitored for each key step of a project. Thank you. And so the hazard level characterizes the proneness to the occurrence of a seismic incident for a given project. And so this hazard level, since the method is iterative, the hazard level can evolve over the life cycle of a project and as new knowledge is acquired. We define 4 hazard levels. The first one is the level 0 with a very low hazard and with no specific recommendation for this type of project other than apply best practice defined for the Paris Basin. Then we have 2 levels for low to moderate hazard, level 1 and 2. And in this case, we need to implement appropriate preventing and corrective measures, such as monitoring, best practice, and so on. And finally, the last level, the level 3, is for high hazard level. And in this case, if it is what's occurring is different than what was planned. And in this case, you need an imperative adjustment of the work program to reduce the hazard level. So the idea is to stop and change what you are doing. Okay, next, please. And so this is the calendar, in fact, of the project and the different evaluation we propose. So in the square, you can see the different steps at which we propose an evaluation. First, we begin by an assessment by well, because well, you drill first one well and the second if needed and so on. And then we switch to assessment by project as you drill several wells. And how it goes, we propose initial evaluation before drilling, then a post-drilling evaluation, and also an evaluation during development that is iterative. You need to do that several times if you have a several cycle of development. And then you switch to the assessment by project with checking for some projects interwell connectivity. And also you do an evaluation during exploitation. And once again, this is iterative. It needs to be every year for 5 years, depending on the level. And finally, a final assessment before shutdown. So that's it for the calendar. Now let's switch the logic tree. So this is the first logic tree, the logic tree for initial hazard assessment. So the idea was to have criteria that were simple and easy to evaluate before any drilling is done, and also to help the operator to have some question to ask to assess his reservoir before doing any drilling. So maybe I will not go into detail of all the criterion, but the first question is related to the plate type, the classification of geothermal type that we mentioned, with the type of fluid circulation, within fault or not. And then we need to know if, depending on the answer, if the geothermal system is already used, and if it's already used and there is no problem, you go directly to the level 0 and you do nothing anymore unless there is a problem. But in other cases, you have to check if there are some signs of circulation in the reservoir and the fault, what are their characteristics. So are there fault potentially hydraulically connected with the reservoir, hydraulically connected to the basement, and also some geomechanical criterion, are the fault critically loaded? And finally, is there some natural seismicity in the area? So once you answer all this, you can have your first evaluation before drilling. And next, if we go now, the drilling is done, and so you can do a better assessment because you have more data. So first, you can reassess are the fault critically loaded, because hopefully you have a better identification of fault and maybe a better constrained local stress field. Also, if needed, if you are in hazard level 1 or 2 in the first evaluation, you had some monitoring done, so you know if there was someone in microseismicity during drilling. So it's the second criterion. And the last criterion was about the injectivity index. So operator need to do some tests to check that. So the answer is it sufficient or not? So you need to do some further development to improve it. So that's the second tree. And the last one is a logic tree during development. So in this case, we have less like some factor to look at before doing some things, such as what is the total net volume injected, and then what you will be doing. Is it EGS or is it non-EGS? That is it stimulation, or do you adapt your well architecture, for example? And depending on that, you define a new level. And this, once again, this tree is iterative. So you do, for example, you can do one cycle of stimulation, and if you do a new cycle, you do this logic tree once again, taking into account the result of your previous stimulation. And next, so what we are doing next is to do some reassessment during exploitation and shutdown phases. So in fact, for each case step, we have some recommendations to reassess the seismic incident hazard level, to check interwell connectivity, so that is for doublet, and also during reservoir exploitation, to reassess the hazard before any major operation and one-time barrier. And to do that, you need to consider the level of seismicity during exploitation and also the evolution of your injectivity index and productivity index. And finally, there is a last hazard assessment prior to permanent shutdown. And then you need to reassess the hazard until it reaches level 0. And when it does that, it is when the recorded seismicity level is identical to the level recorded in the 6 months prior to drilling. So that's it for our logic tree. Next.
Yeah, so I can, yeah, this part is to, so in parallel to the logic trees, so the methodology for assessing the seismic incident hazard, we also provide some recommendation for reservoir monitoring and characterization, and also for controlling the operation. These recommendations are also given in order to help operators, for example, to answer the different criterion of the logic trees. So the first part of the recommendation, we call them reservoir characterization recommendation, because basically we have given recommendation about measures and data which need to be acquired according to the hazard level of the project and also the phase of the project. And these data and analysis and so on will also help to answer the different criteria of the logic trees that Julie explained before. And also in this reservoir characterization recommendation, we have also given some indication about models, and so it can be numericals and analytical models that needs to be realized in order to better understand and try to anticipate the response of the reservoir to the operations. The other group of recommendation is related to microseismic monitoring. So basically, again, what we have done is to propose a strategy about macroseismic monitoring according to the hazard level and the phase of the project. And for what concerns microseismic monitoring, this chart summarized the main recommendation that we have proposed. So basically what we propose is that for hazard level higher than 0, we need to install seismic networks. So in our proposition, we can have 2 types of seismic networks. So a permanent one, which needs to be installed 6 months before drilling, and in some cases, if the hazard is higher than 1, or in some particular situation, especially if we are doing, if we are applying EGS technologies, we need to implement this permanent network with an extended network. So we have to install additional seismic sensors. And as you can see from this chart, depending on the operation phase, the phase of the project, we have several recommendations. We also gave recommendations in terms of technical performances of these seismic networks, depending on the hazard level, and if we are speaking about the permanent network and the extended one. So the extended one, the main objective of the extended network is really to improve performances in terms of detectability and localization, and also to extend the coverage area of the seismic networks, especially, for example, if we start to observe some seismic seismicity, which is developed the farther from the wells, so in an area which was unexpected. And then we provide some indication about the number of probes, the minimum number of probes that are required, the magnitude of completeness, location errors, and so on.
And to finish, we have some recommendation about the operational protocol and specifically the traffic light system. So if you go next. So we provided some recommendation in function of the operation for TLS. So mainly for projects in hazard level 1 and 2. So depending on the phase, we have different recommendations, but specifically in development phase for EGS and non-EGS, we recommend some TLS. For projects without EGS technology, it's a classical TLS with 3 levels, green, yellow, and red. And for project with EGS technology, it's a combined TLS with 4 levels. So I will explain what that is. Just the last point is that if a weight threshold is reached in the TLS, what we say is the project needs to be upgraded to hazard level 3 without any other quantification. So next, to see what are the difference between classical TLS and combined TLS. So the classical TLS are the well-known TLS. So you have a parameter, for example, magnitude. And so if it's above some threshold, you need to do some action within your operations, such as lowering the flow rate, for example, at a certain level, and so on. And so you provide some recommendation. For the combined TLS, the idea is to use some predictive approach, such as MAGAR, for example, and to have an idea of the evolution within time and operation, and to have a combined analysis of seismic and hydraulic variable over time. And so if this combined evaluation is above, once again, well, it's more like a low this time, you do some action. But it's the same idea, but you combine some of your variable, and the main point is that you look over time, what's the evolution. So next. So to conclude our presentation, so next please. So the guide proposes a method for assessing the seismic incident hazard and design adapted mitigation measure. It's a method that is based on logic tree. And it is iterative to do it over the lifetime of the project. And also we provide some recommendation about data to be acquired. We did not detail everything about that, but we also provide a recommendation about seismic monitoring and best operational practice. One point to consider is that the guide only deals with seismic hazard. It does not consider seismic risk assessment, neither governance or social aspect. And some outlook. So now some new actions are in progress to help diffuse and apply the guide. Ineris and BRGM are working on a document to facilitate the application of this hazard assessment methodology and the general recommendation provided in the guide. So it's a document for permit application. The guide is currently being translated in English. And we also are discussing with other European experts who deal with induced seismicity in their country and where other guidelines and our best practice are applied. And the idea is to look for similarities and difference of the proposed approach. Also, all the publication of a guide affects the course of new projects in terms of management, for example, and well, a lot of things. And also, if and all these guidelines have been updated with new acquired experience. Finally, after the Vandenheim incident, the guide provides a basis for good practice because we didn't have that in France for geothermal and it was needed. And now we will need to build on it by keeping improving it, following research advancement and feedback on its application, and also feedback from other countries. So that's it. Thank you, everyone.
Thank you.
Thank you, Julie and Francesca, for this nice presentation. Now we have some time for questions or comments from the participants. If you want to comment or ask a question, please raise your hand or write it in the chat. Anyone has some question?
Can I ask a question, which is very general question? Francesca, what kind of challenges do you see in this kind of monitoring? What is the most difficult part?
In terms of seismic monitoring, you mean?
Yes.
Well, several things, I think, because